frame, to form a frame. And for you to put your FV transformation there, your TRS, okay, for your model. Okay, your object, the vertex that you draw is in the workspace, 3D world. Okay, then this one is the one that we're going to look at in chapter 5, which is your view, your camera. Okay, your view transform, where you put your camera there is, and then your eye coordinate, where you place your eye. Okay, on the camera. So by default, your eyes coordinates, eye space is mapped to your camera. Okay, later your miss will tell you where is the default camera is placing in your OpenGL now. Okay, and you may change it, okay, if you want. Okay, and then the projection transform. So the projection is for the viewing volume. Okay, just like, okay, you place your projector here. Okay, this is what project out on the screen, and this is what you can see. Okay, so you will set your, okay, you will set your coordinates. Okay, your viewing volume, the size, okay, the shape of the viewing volume. So there are two shapes just now, the perspective and also the orthographics. So when you already place your viewing volume, then you have your clip space. Okay, this is the clipper job. Okay, remove all the vertex. The vertex that is outside of your viewing volume, it won't be processed. Future, I mean you cannot see on your screen. Okay, any object if you draw outside of it, then you cannot see anymore. Okay, that's the clip space. Okay, this part is device based. Okay, device independence. Okay, depends on which device that you're going to project or show your output, the display of the graphics. Okay, this one is for normalization. Okay, normalize device space based on your perspective device. So, but for us is your PC screen, your OpenGL window. Okay, the window that we create to show the drawing. Okay, so last, this one will be your window. Okay, viewport is your window, your viewport, your screen. Okay, and the depth range transform. Okay, at the end, what you see is your window coordinates or window space. Okay, in 2D. So here is 3D. Okay, come here. Okay, it's become 2D. Okay, at the end, become 2D on your window. Okay, so this will be the transformation pipeline. So we start with viewing. Okay, viewing is positions your camera. Okay, your view. Okay, now you are 3D world. So which part you want to see? You put your camera there. Put your camera there. Then this one come up. This is what you can see here. Okay, with this camera. Okay, this is your viewing volume. Okay, position the viewing volume in the world. You only can see this part on the screen. Okay, the rest of the thing outside you won't see. Okay, this is called viewing volume. Okay, after viewing, then modeling. Modeling your object lah. Okay, your objects. So for you guys, is draw a triangle there. Your triangle or your polygon. Okay, or your square. Okay, here is just example. This is your model. Okay, it's a basket of KFC. Put inside. Okay, you put this outside, you cannot see. Must put inside the viewing volume. Okay, positioning the model in the world. Okay, put inside your viewing volume. This is called modeling. So this one is model view matrix. Okay, the one that we deal in chapter 4. Okay. Then projection. Okay, projection means you adjust the lens here. Okay, to determine this shape. Okay, whether you want to use perspective or orthographics. Okay, determine the shape of the viewing volume. Okay, that is projection. Okay, last one is your viewport lah. Your window. Okay, your screen. At the end, you see the KFC basket of KFC like this lah. Your model appear on the screen. Okay, projected become 2D. Okay, on the 2D screen. Okay, your screen is a 2D. It's flat. Okay, this is viewport. So 4 step. Remember this. It's very easy lah. Viewing, modeling, projection, and then viewport. So this will be our transformation pipelines. Okay, so in here is your viewing. Okay, your camera coordinates. eye coordinates. Okay, place your eye at the camera there. Okay, this one modeling is your model view matrix. Okay, workspace. Okay, projections. Okay, clip coordinates. Okay, clip space. Okay, projection matrix. Okay, at the end, your window coordinates. Okay, window space. What you see on your window, your screen viewport. Now we learn the default one. Okay, all the way you did your practical 1 to your practical 4. Okay, your default camera frames. Okay, OpenGL that you use is located at the origin. Okay, 0, 0, 0. Okay, and it faces to the negative Z directions. You can see here, face to the back. Okay, that is the default camera. Okay, and the default viewing volume, okay, that you have been using all the while is a cube. It's a cube. You can see the cube here. Okay, that the default size, the length of the cube is 2 times 2 times 2. Okay, XYZ 2 times 2 times 2. Okay, so the default. Okay, default one X, Y, and Z. Okay, 2 times 2 times 2. Okay, that's why you have your, okay, X is also negative 1.0 to 1.0. Okay, your Y also, okay, negative 1.0 to 1.0, and then you have your Z. Okay, also negative 1.0 to 1.0. Okay, so your origin is in the middle, 0, 0, 0. Okay, your camera is here. Okay, facing to the negative Z direction. Okay, so it's a cube. So default projection matrix, okay, if this one, the default one, okay, that you're using, okay, is an identity. Okay, identity. Okay, so any objects, okay, if you draw your vertex between negative 1 to 1, okay, then you can see, okay, the object is inside. Okay, this is what you see on the screen. Okay, you draw a triangle, you draw a circle, okay, inside the viewing volume, then you can see here appear on the screen. So if the objects you go and draw at 2.0, 3.0, your vertex you go and put your vertex 2F or 3F in 2.0, 3.0. More than 1.0 or less than negative 1, then you cannot see the object. Okay, some of you already experienced this. It's cut off when you rotate your cube. You draw 1.0. When you go out, you cannot see. Okay, that is clipped up. Okay, any object you draw outside of this viewing volume, like this object here, it will be clipped up from the screen, so you won't see it appear here on your screen. So your screen is your viewport, or you can see it's your OpenGL window, or it's your projection plan. Okay, your projection plan currently now, okay, Z is equal to 0 because your camera is placed at the 0. Okay, and the default projection here is a cube. The shape of the viewing volume is a cube. This one is orthographics. Okay, orthographics view or orthogonal. Okay, same thing, or parallel view. Okay, we will see the two projections later. So if you want to see the objects, this one must be very careful. Okay, want to see the object, so your camera must face the objects. Okay, must place the object in front of the camera. Okay, some of you will draw your objects, but your camera, okay, is at the back. Okay, your object is at the back of the camera, then you cannot see anything. Happen, okay, be careful. So if you want to visualize an object, means you want to see, so either you move your camera, this is your camera, in a positive Z, this side, Okay, positive z direction, or you move your objects in the negative z direction. Okay, your camera here, okay, your object here. Move your object here, your camera here. Okay, you don't move the balik then you cannot see your objects. Okay, this one is negative z, this one is positive z. Okay, opposites. Okay, here is positive, here is negative. So when you move your camera, okay, that means you are translate your camera frame. Okay, this one we deal with our projection metric. Okay, so all the way that you did in chapter 4, okay, we actually translate the world frame. You're moving your objects. Okay, this guy. Okay. So in order to move your camera, so all your transformations that you learn in chapter 4, your TRS, translate, rotate, and scale, okay, that you perform for the objects, you also can perform for your camera. Okay, you can either move the camera frames or the world frame. Okay, it's work as well. So GR translate F. So to move along the z-axis, this is the z. Okay, negative z. Okay, move in the negative z direction. Okay, you move your camera. Your miss already tell you, you have to move. Okay, one in negative, one in positive. Okay, we will do this and test this later when we do practical. Okay, move until you cannot see. Then you know what happened. As here, this is your camera and the origin. This is your X, Y, and Z. Okay, X, Y, and Z axis. Okay, the whole camera now is at the origin. Okay, when you translate, okay, move in the negative Z already, negative D. This is your Z axis. You move here, so now your camera is here. Okay, your camera coordinate, this is your camera coordinate, X, Y, Z. You see the C there? Okay, it's your camera coordinate. Okay, previously is similar with your world frame X, Y, Z. Okay, now your world frame is here. After you translate your camera here, okay, your camera coordinate will be here. It's different, the origin will be different from your world frame. Okay, so be careful when you move the frame, and you have to specify which frame you are referring to. Okay, you're actually moving the object or you're moving the camera. Okay, and when you move your camera, you also can move your eye, view coordinate. Okay, this is your eye coordinates. Okay, so we don't use X, Y, Z here. So you have your U, okay, V and N. Okay, the three axes, the three vectors to represent your eye coordinates. Okay, so to move the eye coordinate, which is your view coordinate system. Okay, this is the OpenGL commands we call GRU locate. Okay, to move the eye. Okay, and there are 9 parameters here that you can set. Okay, the eyes, first you place the eye first, your eye you want to put where. Okay, X, Y, Z. Okay, then your look. Okay, your looks of this, your eyeball coordinate, up, down, left, right, X, Y, Z. And then your up, this one is for the normal, X, Y, Z. Okay, of the vectors. Okay, but your miss won't ask you to move your eye. Okay, now by default your eye is met with your camera. Okay, you can move your camera but don't move your eye. Okay, unless you really want to move. Okay, to set up the camera, we have the three axes that your miss tell you just now for to represent your eye coordinates X, Y, Z. This is your U, V, and N. Okay, without any transformations, so original is mapped in the original 00, same in your world frame. Okay, world frame. Okay, so you do translate. This is the translate matrix. So your tell you translate matrix. Your TX, TY, and TZ is in the last column here. So you move your I. Okay, your IX, IY, and your this matrix for your n. Okay, with your u and v and your n. So you have the 12 degree to move. Okay, for the GRU look at. Okay, that one is I. Okay, so for now I won't ask you to move the I coordinates in your practical. Okay, we will rather do with the projection. Okay, projection. Okay, so what is projection? Okay, projection will reduce the dimension by 1. Okay, from 3D world, okay, project on the screen, everything become 2D. Okay, screen is flat. Okay, that's why it will reduce 1 dimension. Okay, see here lah. Okay, the 3D real world. Then at the end on your computer screen is a 2D image. Okay, that's the purpose of projection 2. Okay, and convert all your vertex here. Okay, vertices here, come to here, everything on the screen will become your pixel. Okay, pixel. So we look at these 2 types of projections, perspective and orthographics. Okay, the big difference, okay, one, you can see the changes of the size. Okay, the scale of the size of the objects with distance. Okay, that's perspective. Okay, object that far away will look smaller, object that close to you will look bigger. Okay, so for orthographics, object will not scale with distance. So even though they are close to you or far to you, it will look the same size. Okay, size same. And that's orthographics. And we can see the more clearer pictures. So for orthographic is meant for 2D lah. So these are orthographic view. You can see here example. Okay, 2D games. Okay, this is perspective. Okay, perspective you see 3D. Okay, so you can see the people here close to you look bigger. Those like at the back here. Okay, those people are smaller, very small because they are far from you. Okay, object scale with distance, 3D perspective. Okay, perspective view. Differentiate. So with this one now you can see the illusions of the darkness lah. The object that far from you will look smaller. Okay, so the square here is big. Okay, the pot here is big. Come here. The pot here is small. This is perspective view. Okay, so orthographics and perspective view, both views still using now because we still at 2D. Okay, not all 3D. We still have 2D. Like 2D you can use to do menu. Okay, in the game also got menu, got screen, got manual. Okay, all this can use orthographic view. But if you want 3D, then you use perspective. Okay. This one big pictures. You can see very obvious difference between the 2 view. Can? You see this one orthographics. Okay, this tree is near to you, this tree is far from you, but same size. Okay, you see the track, this one. Okay, the train tracks are still, the road are still the same size. Okay, even though the distance are not same. But this one you can see perspective. Okay, object shrink in distance. So the front part now bigger and then the last part here looks small. Okay, so you know this tree is in front. It's near to the viewpoint. It's near to you. This one is far. This looks small. Okay, you can tell the distance here. Okay, in perspective view. Okay, but for orthographic view, you cannot tell the distance. The same size. Okay, this is the big difference between the 2 view. So this is the nature of perspective view. Okay, this one will happen later when you do your assignment. Okay, you draw in auto view. Okay, all your shape is so nice like this. Your cube, your quad is look like this. Exactly same size with different z value. Your cube. Then when you change to perspective view, you see the shrinking happens. become like this, then you say, Miss, my robot look weird. Okay, don't worry, this is the nature of perspective. It's really like this. The front one will look bigger and the back one will look small. Okay, and don't make your Z too far when you draw your robot. Don't make your Z value too far. Then you see the string is very obvious and very serious. Okay, the front body is so big and then the back body is so small. And then when you turn the side, you see the string happens. Okay, that's perspective. We will test later. You can see your practical 5. So for projection, we are dealing with GL projection matrix. So when you do transformation, now you have to specify. Now you have to move your projection, transform your projection, or you want to transform your model. Okay, last time we didn't specify, so by default it will transform your model. Okay, so projection used to convert from 3D to 2D, and used to convert from eye coordinate to click coordinate. Okay, when you click, immediately remove all the coordinate that is not inside the viewing volume, and it will process and it will show on the screen. Okay, the grid coordinates are transformed to NDC normalized device coordinates. Okay, based on the device that you use. Okay, it will divide with the normalized value. The W here is the control value, the weight. Okay, for the device. Okay, so by default, okay, so it will 0001. Okay, the last rows of your matrix. Okay, unless other different device got different format lah. Okay, so you can see here from your object coordinates x, y, z. Okay, the W is the 4 components. That's why your 3D, but your matrix is 4 times 4. You have the homogeneous here. Okay, the 4 values is for you to do the normalization. Okay, we have model view matrix. Model view matrix, our chapter 4. Okay. Okay, the matrix stack. Okay, then you place your eye coordinate, then you have your projection matrix here. Okay, after projection matrix, you have your grid coordinates, then you do your NDC here, normalize coordinates. Okay, normalize device coordinates. And at the end, this is your viewport, your window. Okay, your window coordinates. Okay, this is the transformation pipelines with the matrices and the coordinate. Okay, now see the shapes of the projection. Okay, the different shapes. Okay, these are the projection line. You see the line here. Okay, so for orthographic projection lines are parallel. Okay, parallel. Okay, must draw the projection line. Okay, sorry. Okay, so this is your objects, and you have your projection plane, this one, or your viewport of what you can see on your screen. Okay, you see the object size. Okay, this is the object size. Okay, the cube, your cube is like this, front and the back same size. Same size. Okay, very nice, the cube same size. And because of the projection lines are parallel, okay, for orthographics, we have this DOP, means directions of projection. Okay, different from perspective. So perspective, your projection line, okay, you need to draw and meet at a single point here. Okay, single point here. Okay, and this point we call it as COP. Okay, center of projection, COP here. Okay, and you see the object size. So this is a cube, the same cube as this one, the same objects. But on the screen, okay, on the screen you can see, okay, the front one, okay, the front parts will be bigger and the back one will be smaller because due to the projection line. Okay, so your cube will look, the shape not preserved. The front one will bigger and then the back one will small. Okay, that's perspective view. Okay, that's the natures of perspective view. Like you don't say, Miss, my cube look very weird, my robot look very weird after I change to perspective view. Doesn't matter. Okay, you have to show that. Okay, how to build the projection matrix? Okay, projection matrix similar to your model view is also 4x4 using affine transformation with homogeneous coordinates. Okay, we see one by one the projection matrix for orthographic and then the projection matrix for perspective. We'll see later. Okay, the orthographic projection, so projection line, okay, when you ask to draw orthographic projection, must show the projection line that are parallel. This is the features, okay, and the shapes of the viewing volume is a rectangular parallel pipe. Okay, this is the shape. Okay, so your default viewing volume in your OpenGL is a cube, it's a parallel cube. Okay, so it's an orthographic. Okay, so you see these objects. Okay, you orthographic projection. Okay, you can see something like this. This is the front view. So we have different view here. You can see. And these are orthographic view. Okay, front view, the same object are front, the side view, and the top view, or 2D, 2D. Okay, but you have this like look like a bit 3D. Okay, this is called isometric view. Or sometimes you heard people say 2.5D. That is referred to isometric. Okay, what is isometric view? Okay, isometric view means you actually put your camera up and then you look down 45 degrees. Okay, then the 2D image will have a little bit of illusions of 3D, but the object is still 2D. Okay, it's not 3D object. That is isometric view. Okay, so for orthographic view, so object will appear same size, okay, despite their distance. So there will be no changes of the size of object, even though you move it close or far. Okay, this is your screen. Okay, so your object here in front or your object at the back, far away. This one close to you, because your projection line that are parallel. So at the end, this is your object size, same that appear on the screen. Okay, this is orthographic. Okay, what are the advantages? Okay, people still using orthographics. Okay, because there's no changes of size, so there will be no distortion. So it will preserve all the angles and all the distance of the objects. Okay, shape. Okay, the shape is still exactly same. Okay, no changes. So this is good for measurement. Okay, measurement. So you can see a lot of building plans. Okay, this building plan, floor plan. Okay, or the manual or 2D or screen UI. Okay, is still using orthographics because of this nature. Prefer both distance and angle, and the shape is and good for measurement. So these are the advantages of orthographic view. Okay. So what the disadvantages? Because it's 2D. Okay, it's 2D, so cannot see what object really look like because many surface hidden from the view. Okay, just like your cube that you draw, you only see the front face. The back face you cannot see. Okay, because the back face is hidden from you. Okay, the object that at the back you cannot see. Okay, just like your mistest. To draw the triangle, draw the quad, and then move together, and then you see the triangle at the back at the quad. You cannot see. Okay. So that's why people try to use isometrics. Isometric. So this is isometric view. You can see from the top and then look down 45 degrees. Okay, but the objects here, all these image or sprites, we call it as sprites. Okay, pictures here all still 2D pictures. Okay, it's an images, but with the isometric view, play around with the camera, then you can have a bit of 3D feel, illusion of that. I mean, you can still see the object at the back. This one in front, this one at the back. this isometric view. Okay, but somehow this one does not provide realistic and a sense of 3D. Okay, these are the main disadvantages of orthographics. Okay, not realistic and then don't have the sense of 3D. Okay, that's why we have perspective lah. Okay, so now we see the projection metric for orthographic. Okay, this is your frame, your world frame, XYZ. Okay, XYZ. So by default, this is the default one. Okay, you see this is the cube. Okay, -1 to 1. Okay, for your X, Y, and Z. Okay, X, Y, and Z. So all -1 to 1. Okay, and your world frame now is in the middle. Okay, so this is your origin in the middle. So currently your miss just now already say your camera frame okay, is in the origin here. Okay, it's here. So if you normalize the device, okay, you will move up your world frame. You will move it out, translate along the D in the negative Z. Okay, then it's go up. Okay, where it is LTN, okay, left, right. Okay, L is left, R is right. Okay, we have -1 to 1. T is top. Okay, it represent this cube. Okay, T is top and then the B is bottom. Okay, top and bottom. Okay, top and bottom, and your N is near. Okay, your F is far. Okay, near far. So currently your left, right. Okay, -1 and 1. Bottom top, -1 and 1, and your near far is -1 and 1. Okay, which is this one. Okay, the default one. So in orthographics, all the X, Y, Z, E, or I components in the I space are linearly mapped to the NDC. Okay, this one. So if you want to move, okay, what you can do, okay, you can scale the rectangular volume to the cube, then move it to the origin and use the linear relationship. Okay, to map, to do the NDC normalizations to get your normalized coordinates from your I coordinates. Okay, your XN, your XE. Okay, we have the formula here. Okay, so you normalize your X equal to your 2. Okay, divided by your right minus left. Okay, R and L is right, left. Okay, multiplied by your E. Okay, your I coordinate of your X. Then your right plus left divided by right minus left. Okay, this is the formula. Okay, don't worry, you don't need to memorize or hafal the formula. Okay, the formula is given. Okay, to map for the XN. Okay, for the I coordinate using the left right values. So currently your left is -1, your right is 1. The default one. Okay, same thing for the Y. Okay, just change same formula. Just change the LR to TB. Okay, top and bottom. Top, bottom, top, bottom. Okay, so in the default viewing volume, your bottom and top is also -1 and 1. Okay, and then Z. Okay, for the Z, formula also same. Just change your, okay, just now your top, bottom. Okay, this one is lower. Okay, you change to near and far. Okay, N is near, F is far. Because we want to see the projection matrix. So since the W component is not necessary, okay, for the normalization, the W, so the last column there is still constant. Okay, 0, 0, 1. Okay, so this will be the projection matrix for orthographics. Okay, orthographics. So diagonal referring to the size. Okay, so this is the size for x, size for y, and size for the z. So x1 is your right minus left, r minus l for x. Y, so top minus bottom. Okay, 2 divide top minus bottom, and your z is front minus near, far and near. Okay, so this one is the size, and this one is the translator, the I coordinates. Okay, so you put here, okay, for left, right, top, bottom, and your near, far. So when you see this, okay, you should know this is orthographic projection metric. Okay, later we're going to differentiate this with the perspective projection metric. Okay. So what happens? Well, in OpenGL, okay, you don't need to declare this matrix on your server, this orthographic projection matrix. So already have the command. Okay, one command only, very simple. Okay, in the library already provide you to create the orthographic view, just call GRAuto. Okay, GRAuto, and then you pass in these 6 parameters that represent this cube. Your left, right, bottom, top, and your near, far. Okay, of this cube. Okay, bottom, top, left, okay, left, right, and near and far. Okay, just set this cube, your viewing volume of the orthographics. Okay, currently your default one is negative 1, 1, negative 1, 1, and negative 1 and 1. Okay, this one left, right is your x, negative 1 to 1. Bottom, top is your y, now it's negative 1 to 1. Your z also, near, far is negative 1 to 1. So any objects like this cube, you draw inside this viewing volume, you can see. If you draw outside, you cannot see lah. Okay, toward your viewpoint. So we will test this later in our practical class. Okay, now you go for perspective. So perspective is model how a camera take pictures. Okay. So parallel lines on the object at the end will converge at the single point here. Okay, this is your projection line. And meet at the single point here because as your P that at your eye here. Okay, the same objects. Okay, you project, this is what you see. Okay, so okay, you can compare this diagram with just now orthographic view. So object that further away will give smaller image because due to the nature of the projection line. Okay, so object close to you bigger, come to you small. Okay, small. Okay, size change. Okay, so this one different with the orthographic. Okay, orthographic, parallel, projection line, so size same. Okay, so now you observe the view. So these are the view from the orthographic, front, side, top, isometric. And now we go to see the view of perspective for the same objects. Okay, how it look. Okay, this one is the perspective view. Okay, even though you are in front, front view, you can see it's a change size. Okay, this one will look big, bigger compared to the one at the back. Small, smaller, smaller, smaller. Okay, so if you see your view like this, is correct for perspective view. So advantages perspective view. Okay, object far away. Okay, are projected smaller than the same size. Okay, size of the objects closer to the viewer will diminish. Okay, diminutions. Okay, you see here when this perspective view. So this gun, long gun here. Definitely this part will look bigger, and then you come here, this part looks smaller. Okay, this perspective view. Okay, objects, same people that near to you will look bigger. Okay, the people that far will look smaller. Okay, this will make it look realistic. perspective view. Advantages. Okay, any disadvantages, perspective view? Okay, equal distance along the line are not projected into the equal distance. So it depends on how you define your distance on your screen and the distance in the real world. Okay, maybe different. That is called non-uniform. Okay, you just know which one is far, which one is close. But how far, how close, you cannot tell. Okay, so because it's different from actors, your 3D space, and each of them may use different scale. Okay, or viewing volume size that we will fix, we will see later. And definitely perspective is more difficult. Okay, compared to your auto. Okay, but with computer it's actually not so difficult. So just now auto is only one command, GL auto, but your perspective got two commands. Okay, two commands. So the first command is called geofrustum. Okay, geofrustum. Okay, two commands. One is called geofrustum, and another one is called GeoU perspective. Okay, geofrustum is to set the viewing volume. Okay, similar to the GeoAuto just now. Okay, this shape. This one viewing frustum or viewing volume. Okay, so you have to pass in. Just now in your auto is your left, right, bottom, top, and your near far. Okay, so in here, perspective, your frustum. So your left, right is actually similar to your X-min. Okay, X-min and X-max. Min and max for your X. And then your bottom top is your Y-min. Okay, and Y-max. Okay, this one, near far, Z-min and Z-max. Okay, the front one here, this is your Z-min blend. Okay, your near blend. Okay, the one at the back here, bigger, a bit. Okay, bigger. That is your Z-max. Okay, your far blend. Near blend, far blend. Z-min, Z-max. And why got negative here? Why you put negative here? Okay, this one is geofrustum. Later we're going to use this value. Okay, it's because your camera is facing the negative Z direction. Okay, and your camera is at the 0, 0, 0 here. Okay, that's why you put negative here. Okay, called negative Z-min and negative Z-max. Okay, then we have GeoU perspective. Okay, more parameter to set after you set your viewing volume. Okay, you use GeoU perspective to set your this angle that we call as field of view. Okay, field of view. This one is Y. Okay, FOVY. So it depends on your window resolution. This one your plan, your projection plan. Okay, try to map your field of view Y with your height. Okay, this is your height of your window, your window or your screen. They're going to show or your project your objects. Okay, so window resolution. Okay, your height and your width. Okay, second one is your aspect ratio. Okay, aspect ratio means your W over your hash. Okay, W divide your hash. Okay, that will be your aspect ratio. Okay, then set your near. Okay, near is from your camera. Okay, to your near blend. Okay, and then your far. And where you want to put your far blend. Okay, from your camera. Okay, near and far. Okay, so you need to use two commands, geofrustum and GeoU perspective for perspective view. So photographic only use GL auto. Okay, all this command later we do in practical 5, in the practical class. Okay, so now we want to see the projection matrix for perspective. So many 1 minute only. Cannot. this one also need to explain. Okay, for the perspective projection matrix, I think your miss will continue next class. Okay, because now it's already 59, it's already 3 o'clock. Okay, your miss got meeting at 3. So I will stop here. Okay, perspective projections. So for the matrix side, this one just theory. Matrix side. Okay, we can still do practical 5. Okay, just want to see the formula. Okay, how you come out this perspective projection matrix. So it's different from the orthographic matrix just now. Okay, so this last part, your miss will continue next week. Okay, so I will stop here. Okay, that's all for today. Okay, we stop here. Slides. Okay, continue next week. Okay, thank you class. Okay, make sure you list down your attendance. Outside. So the guys